welcome everybody. There's a lot of really awesome talks in this time slot, so thank you for coming to this one. And if you didn't mean to come to this one, now is your time to make your way to the exit quietly. This talk is called We've Got Your Back, Engineering Optimization Ease. And if you don't mind, if you have a seat next to you, if you could scoot towards the aisle so people can jump in on the end quietly, that might be helpful. And then you make new friends and get new lawsuits. It's great. So optimization. Is kind of known in some circles as a byword for that thing you do at the end where you have to cut a bunch of corners and cut a bunch of quality in order to eke out a frame rate, or it involves your graphics engineer staring at a lot of graphs and frame breakdowns and smacking their head against them. But I'm hoping that after today, you'll see that optimization doesn't have to be that way. We're going to go over some of the things that Intel and EPYC have been working on for a long time and are continuing to work on today, largely to work to bring some of those common bottlenecks back into the core engine to get them out of your way before you even hit them. So why do we care? Personally, I care because this is my job. I'm a game performance engineer at Intel, which is a completely made-up title, but it very accurately describes what I do, which is I am responsible for the performance and quality of Unreal Engine on Intel hardware. So it's my job to make sure it runs well, runs effectively, and runs its best, especially on low-powered hardware, but really for everyone's hardware, because that's what it's all about. Intel and EPYC have been working together for a while on all of this stuff, so a quick shout out to Jeff Roos and Rolando, who worked on this presentation with me as well. But the major thing is there's other people like me at Intel. We do a lot of developer relations engineering, which is the technical term for what we do. Some of you guys may have worked with an Intel engineer on your game for specific bottlenecks that are in your game. But this is kind of all about how we bring those bottlenecks back to the main engine. So why do we do this? Whenever we do this, we're benefiting every game that licenses the engine, as well as every other application that uses it. UE4 runs on more hardware, which EPYC likes, and our hardware looks better for being able to run the engine. We're also a pretty significant share of the CPUs used in gaming, so we're going to talk about how to make use of that. And these optimizations are always designed to do no evil. They are at least parity with everyone's hardware, and for the most part, we try and make everyone run better. Rising tide lifts all boats. So these are optimizations you can use from the high end down to a phone. The nice thing, too, is hopefully we and EPYC have some common goals, and hopefully you guys feel the same way, which is we care a lot about scalability, making sure that this experience can go from the low end to the high end, and that as many people as possible can play and love your game. And also about exploring that next step. So what are the leading edge APIs exploring, and what kind of technology are they making available for us to explore? So today we're going to go on a little bit of a journey. We're going to walk through mostly by bottleneck with some side steps. So we'll talk about CPU considerations, do a little bit of an overview of the UE4 threading model for those who aren't familiar, talk about what to do when you want to shift work from the CPU to GPU and otherwise, move into the GPU bottlenecks, and then talk about where we're going to go next. I can't have any memes in here because we're in the EU. So I give you my programmer art. These are potatoes. We're going to talk about a game called Potato Champion. So if I'm referencing potatoes in our workflow, that's just that is meant to be a potato. I am very clearly not an artist. While we're going through all this stuff, I want you to think about some kind of common themes that are going to come up over and over again. So what we want you to be able to do is trade work between the CPU and GPU depending on your bottleneck. So when your GPU bottlenecked, maybe move things over to the CPU and vice versa, parallelizing wherever possible, whether that's on the CPU or GPU, and spending your processing time where and when it matters. So getting things offline if possible, or just putting them in the right place. Let's kick this off with CPU optimization. We're going to pretend right now that our Potato Champion game has a render thread bottleneck. But Kelly, how do I determine if I have a render thread bottleneck? Haha. So I stole this slide directly from my presentation last year, so throwback for all of you that were here last year. essentially, the first place to go is just throw down a stat unit. You're going to get your game thread time, your draw thread time, your GPU thread time, and your RHI thread time. Because games are essentially a pipeline, things start on the game thread, move to render, move to the actual GPU. We always start kind of on the game thread, move to draw, move to GPU when we're looking at the bottlenecks. So if you're starting on the game thread, you need to get rid of that before you can accurately assess the performance of the rest of the pipeline, or you're going to have bubbles. Because I like breaking all of the rules, we're going to start with a render thread bottleneck instead. So what this would look like is you would see your draw time being kind of around the same time as your frame time. So in this case, our frame time is 9 milliseconds. We're going to pretend our draw time is 9 milliseconds. Normally, when you start thinking about render thread bottleneck, the first thing that an optimizer or graphics engineer is going to throw at you is, why aren't you batching or instancing? So we're going to draw our potatoes here. What batching is going to do is essentially we're reducing the number of flushes between draws. So we're trying to group draws that are using similar materials. So in this case, we have brown potatoes and yellow potatoes. And rather than switching in between each draw, whether we're drawing yellow or brown, which means we have to flush our entire shader pipeline, draw the other one, flush, switch back, what we want to do is we want to group similar materials and draw them together so that instead we only have that one flush as we switch to the other color. In Unreal, this is largely done for you. One of the things that you can help it to do is by using, reduce the number of materials you're using in a mesh, use texture atlasing properly, but overall, it's kind of something that's out of your hands, or your artist is just going to get mad at you. The other thing you can do is use instancing wherever possible. This will actually reduce the number of draw calls, which is very handy. And so in this case, instead of having 2 draw calls, if they're the same instanced mesh, then you can just combine that down into 1. You're still going to have the same GPU time because you're still drawing both of them, but at least your render thread bottleneck is going to go away. So these are kind of the first things that we toss out when we think about these things. But if we step backward and think about from a high level, if we're early in our game and we can think about what API we're even choosing, the other answer we throw at people is use DirectX 12. DirectX 12 is much more naturally parallelizable, and because of that, you're going to have a lot fewer bottlenecks on the render thread. The main problem is that DX12 isn't a natural adoption. It's a very different model than DX11. With the DX11 driver, the reason you have that render thread bottleneck is because we're doing a ton of optimizations in the driver for you. And now, because we have DX12, all of those optimizations are the responsibility of the developer instead, which is the Unreal Engine guys. So because of that, getting that up to performance parity is a process that's been a little bit more slow going. That's largely my main project right now. So if you have feedback, let me know. But one of the big things we've been doing too is improving the performance of our driver in terms of shader compilation and runtime efficiency to make some of those new features that come with DX12 more available. So things like variable rate shading and ray tracing, we need to have the baseline performance in order for you guys to feel comfortable to move there. So other than those kind of optimizations that are ongoing, this one you guys kind of get for free, which is use the RHI thread. What is an RHI thread? This is the render hardware interface thread that is brand new to 421 or 422, which actually can parallelize DX11 submission, which that's not a naturally parallelizable API. So let's go through that. We're going to do a nice high-level overview of how threading works in Unreal, specific to the render thread. So we have our game thread, our rendering thread, physics, and audio, and then we have a bunch of task graph threads that are spawned depending on the amount of available cores you have to process all of that. So our game threads are always working on N, and then as it gets enough information to submit to the render thread, it starts submitting that there, and so they kind of overlap in execution. Physics does its own thing because it's got its own tick, and the audio generally runs on the same frame. Let's look at rendering a little bit closer. So the conceptual model is that as those things get ready on the game thread and we know exactly what we're going to draw, we can start sending it over to the render thread for processing and then submission to the GPU queue. One of the nice things that Rolando did is change that enqueue render command so that instead of being a macro, which you can't put a breakpoint in at all, it's, I love macros, it's now Lambda as of 422. So you can actually put breakpoints in there. And what that means here is you can see exactly when that submission is happening from the game thread to the render thread. So that internal enqueue render command is happening on the render thread, and that outer loop, the enqueue begin render frame, is happening on the game thread. So you can see exactly where that transition happens. All right, so we're on the rendering thread. We have a command that we are working on, which is called allocate render target. And we're going to talk through kind of the original current model pre-422. So the render thread is running command A. It then needs to translate this command into whatever graphics API that you've told it to use. So let's say that you're using DX11. In this case, we're going to take that, and the RHI is going to do RHI begin render pass, and that will resolve into D3D11 context OM set render target. But essentially, there's this idea of the command gets submitted, and then it gets translated. And then we submit another command, calculate uniform buffer, and then that gets translated, and so on and so forth. So we have this kind of interleaved process that's happening. Basically, the problem with this is because we're interleaved, we're getting some kind of thrash in here. So one of the things that we did to improve that was, all right, well, let's try using a command list with this. So instead of translating right away, as soon as that rendering command is submitted, we add it to a command list. And then instead of translating it, we move on to the next command and the next command and next command. Essentially not executing the DX stuff, just the render level stuff. At some point, we'll either run out of memory in the command list, or you've defined a safe point to switch command lists and start processing, and then we move on into the translate step. So now we translate A, and then B, and C, and D. And this actually, it looks like more work, right? Because we now have added this overhead of having this extra little bit of memory on here, and we're writing to it, and we're reading from it. But the thing is, now that these steps are kind of chunked, the rendering code is more localized in terms of like the actual code and the data that it's touching. And because of that, and for the translation step, the RHA command list memory overhead is like really small, and it's still very local. So actually just doing this and making these more chunked, we end up with like 5% render thread performance improvement already. But the best part is that now we have these two processes decoupled, and so we can just move one to another thread. So we've added an RHI thread. And what you can see here is that we can start processing before we finish submitting. So we're reducing some of that latency there. And we have an overlap. So we have a translation happening on our second thread, our RHI thread. So the only thing this thread does is crawl DX directly. The only thing the other thread does is set up the rendering commands and submit them to the RHI command list. So we've consumed all of these commands until we finish up. So you can see here now we have this 3-thread model. We have the game thread working on frame N, rendering thread still working on the same frame with a little overlap, and the RHI thread with a little overlap. So it looks like from this view that we're getting increased latency, right? Because we're submitting at later stages, but we actually aren't adding any latency because normally this would just be more time being spent on the rendering thread. Like that translation step would have to happen in synchrony. It is new for DX11, and it is available in 422. We also have a patch for people who are feeling adventurous. But basically decoupling the RHI command list, that way it allows us to do some other fun tricks, like going wide, doing a parallel front end. So not just having those DX commands consumed in a parallel way, but also generating them in a parallel way. So some good candidates for this are your velocity, your depth prepass, your base pass. These are all times when you can just submit all of these commands at once. So in this case, we're submitting A from the rendering thread, and then we actually record these sub-command lists on some parallel threads that we've spawned up. And these can be recorded in any order, but they're guaranteed a translation order. So we have this kind of join, that's what those black vertical lines are that happen, that help maintain the synchrony. So that subcommand list from that one thread is going to happen before, like after B, but before E, and so on. And then, of course, we join the commands before F. So how does this look on our RHI thread, which is doing the actual translation? As soon as we have that join from the last one, we can start executing it. So A is in the command list, we can start consuming that. When we've joined B, C, D, and E, we can start consuming them, and so on. So we're reducing a lot of the bubbles that normally happen here. Also, the nice thing too is this all translates to DX12. So you can imagine with DX12 where you can have multiple RHI threads, we can now actually translate those commands in parallel as well. So let's talk about some other places on the CPU that you might be hitting single thread bottlenecks. One of the, in this case, like perhaps you're game thread bound, which is one of the things we'll talk about. But the main thing that I want to talk about, which if you guys haven't seen is absolutely amazing, is the chaos physics. The demo at GDC was amazing. There's a talk on it tomorrow, which if you're not coming to, you definitely should. Physics is a fantastically parallelizable problem when set up correctly. So this is a great way to use up your CPU really, really nicely. We worked really hard with Epic to optimize a lot of the lower level solvers, choose the right data structures, work on thread parallelism, to make all of these things work really naturally for anyone who tries to use them. Some things that may seem obvious, but kind of hit you in the gut after a while. C++ is not a naturally parallelizing language. There are things you can do to indicate to the compiler what you're trying to make SIMD, or single instruction multiple data, but they're dependent on the compiler version or the intrinsics, and then you change compiler versions, you have to rewrite all of that code, which is a pain. So we used something called Intel ISPC, which I'll explain in a second, that does a lot of that for you. Also, there's some data structure things. So even though you may think a tset would be great for finding uniqueness, you can just do a tset.contains. One of the things we found is we were spending so much time in the hashing function because we were doing it so much. This is one of those places where you really want to let the data guide you. And in this case, it was a matter of the data said, hey, this is actually faster if you do a TRA sort and remove swap rather than keep doing this tset.contains. So that was a place where our tools really saved us. Also, a parallel for, while seems like the natural idea to use to make things go wide, can also hide a lot of really bad cache behavior. So again, keep an eye on your tools, watch what they're telling you, and when possible, like batch a lot of those jobs, or even sometimes it's just better to run single-threaded. So, what is ISPC? It is a terrible name. It is Intel Single Program Multiple Data Program Compiler Integration. So it has a terrible name, but it's actually an amazing piece of technology. It's one of the things that we're actually can really get behind in the industry because it just makes sense. The idea is that all of those compiler intrinsics that you had to do very specifically for very different compilers and all of that is gone. You just write it for the ISPC language, and it does all of that for you. So CPUs have had these vector compute units since like the early 2000s, which basically means like they can do up to like 8 floating point operations at once instead of you having to do that like once, iterate through that loop 8 times. The problem, though, is that it's so hard to write it in a way that the compiler understands and does correctly, that people spend more time debugging it than it's worth the performance they get back out of it. So essentially, ISPC gives you implicit parallelism. The SIMD lanes are going to act very similar to a GPU shader with a few caveats that I'll go over. You write it once, and you can compile it to whatever instruction set, and it does have like an auto detect, so it'll see what your CPU is capable of, and then compile to the correct language for that CPU. It also, so we use this in Chaos, but this isn't specific to that system. This is something that we'd like to see a lot more people who are coding in C++ in Unreal getting to take advantage of. So this is coming shortly to the engine. Again, keep your eye out for patches and current and future engine releases. It's really easy to do. You just include it in your build.cs. It generates these files that you include with a project, and the Unreal Build tool has it integrated, so it should be pretty natural. We also have a GDC talk about some good places to use ISPC, but just to give you a hint, it's really good for dense compute workloads, anything heavy math like physics, intersection testing, cloth or CPU vertex transforms. It works really much better when you have contiguous memory to read from. And like manipulate and store like in a T-array or something like that. It's also best when you don't have a lot of data dependencies that you then have to branch too much on. Think like normal shader code things. It's especially useful when you combine it with Parallel 4 and batching too, because they all do kind of different things. So just to properly show you how not scary this is, the code that you see on the left there is our ISPC code. So essentially all you need to do is include that header and denote the correct like uniforms. Uniform or varying, it's the same as like scalar and vector. And it compiles into those vector instructions on the right. So relatively easy to play with. We got a lot of gains in a lot of different simulations very, very quickly. So keep an eye on that, and you're welcome to experiment with it. Another game thread optimization or general CPU side optimization that people may not think about a lot is CPU particles. GPU particles can give you such great volume and really bombastic effect, but the nice thing about CPU particles is you can do more with their collisions, you can do light emission and those kind of things. We found a lot of low-hanging fruit in the CPU particle simulation, so we figured we'd go ahead and pick that for you. So we have about 4x throughput, what we used to be able to do in terms of CPU particles. It's great if you have a situation where maybe you need to back off some of the GPU work and you have some CPU headroom, might be a good place to start looking at that. Because this is the older system, it's something that we still care about because we work with licensees who are still using Cascade instead of Niagara. Not necessarily something that'll go into the engine, though we have fingers crossed. But we do have a patch available, so we'll get that up on our GitHub once legal gets out of our way, and it will be open to all of you guys. So let's talk about shifting workloads. Some tools to guide you, because again, always let the data show you where you want to go. I can't count the number of times where I've optimized something really, really well only to realize that I didn't do this step. And I optimized the wrong thing. So there's a lot of Unreal built-ins that are great. We just talked about StatUnit, StatGPU, all of the stat systems, the frame capture system. I'm very excited for whatever tools they have coming shortly. I think that's 423 they said. I have great hopes. What we use a lot is Intel graphics performance analyzers. I meant from Intel, we have to shell the tool. But it's also a really good tool, so it's kind of, if RenderDoc is for debugging, then GPI is really great at performance. I've even given it to tech artists too, if you want to start getting them into some performance mindsets. It's very friendly, very obvious when something is going awry, how to pick that up quickly. They also have a system analyzer that is kind of an outside-in profiler, so it doesn't need to know much about your game, which is great because it works on release builds, so you can get an idea of their performance as well. There's also, you can go to OS specific tools. I largely work with Windows, so I'm using Windows performance analyzers, and when I really hate myself, GPU View. It's beautiful, but horrible. When you're ready to go deep on the CPU side, there is Intel vTune. So vTune is a very deep CPU performance analyzer, originally created for more high-performance computing workloads. So there's still some kinks to work out with gaming workloads, but we welcome your feedback and we'd love to make the tool better. I largely use it for advanced hotspots, which is great. It tells you what functions you're spending your time in, but there's also a really awesome locks and waits analysis that can help detect some thrash. We also integrated all of the ITT notify events into like the stat named event system in Unreal at 4.19. So you can take advantage of those things. Also, vTune used to be a paid tool. It is no longer a paid tool. It is completely free. I think it's like a 1 or 2 click download. So you're more than welcome to take advantage of that. When we're talking about moving work, another thing you might have is maybe you're doing too many lighting calculations on your GPU, which the simple answer is, of course, like bake whatever you can bake. This was not a potato joke, but it just fits so well. The light baking system is actually based on Intel Embry, which is and has been for a while. At the time, has made it a lot faster. It's something we actually have a new version of Embry that should improve performance as well. We're working on that update right now, so again, stay tuned. Should be out shortly here. But under the hood, essentially, this is doing really nice full CPU parallelization as well using ISPC. So because ISPC is essentially just this tool to make things parallelize really well, you'll notice we use it for everything. And other than that, yeah, it has made lighting builds like 2.5 times faster in the past. So this is something that you guys should already have using for free, but keep an eye out for the new update and let us know what you think. Another problem, maybe you're using texture formats that aren't compressed. I don't know why, but so wherever you can, compress your textures. Tiny potato. The texture compressor that Unreal uses is actually the ISPC texture compressor, in case you're noticing a theme here. So it's wicked fast because it just goes very wide again. And this is one of those things where it's like 115x performance improvement over some previous versions on Intel hardware. It's very fast, but it's also something that like we like to keep updated. So if you guys have used it and seen problems with it or have suggestions, we'd love to hear that. So just a quick further vote for texture compression here. Your original image is on the left there, and on the right, you have the image that's compressed to the ASTC format. So we've gone from 12 megabytes to 1.8 megabytes, and we're still maintaining a lot of quality. You're welcome to take this image and shake it at artists. Another problem, maybe you have too much occluded geometry going on your GPU. Like you have extreme GPU geometry bottlenecks on the GPU. So I would like to introduce you to our friend software occlusion culling. There's a couple reasons you might want to try software occlusion culling. You have way too much CPU to use, and your GPU is dying. Or you just want to make a system that is more flexible, so you can call on the GPU or call on the CPU. It depends on where you want. The other really nice thing about software occlusion culling is that you don't have the 1 frame delay. So that kind of white flash, you're also giving fewer potatoes to the GPU. That's my beautiful bow. So if you ever see that white flash when you're moving really quickly, and it's because the occlusion test is failing, because you have that 1 frame delay on your occlusion test. So the technique that we have is called masked occlusion culling. Essentially what you do is you're doing basically is CPU rendering to a really low-res depth texture that we then splice into tiles and then give a tile to a task graph thread. They're bedding all the tiles and then using ScissorX to clip everything. And essentially what that gives us is all of this really nice guaranteed no false positives geometry getting sent to the GPU. You can use this with just your baseline geometry. You don't need to have nice occluder geometry or occludee geometry. but it is, of course, going to help performance a lot if you do. One of the, clearly, I don't know how many people have a 10-core system, but that's like 1/20th the draw calls that there used to be submitted. So definitely something to think about if you're noticing a lot of geometry bottlenecks. Then also something to think about, again, a matter of watch your data, see what's happening. This is going to cause slightly more CPU. Overall, we found it to be a win for maybe like 50% of the games that we work with where it's worth taking that hit. So maybe try it out. It's, again, currently available a patch, shortly a GitHub branch, so you can try it out for yourself. And GPU, exciting. So we figured out that all of this work can't be shifted off the GPU anymore. We're stuck here. All of everything that needs to be rendered is getting rendered. So you would know if you have a GPU bottleneck if basically your GPU times, your game time and draw time are below your frame time, but your GPU time is the same as your frame time. So one of the big hammers for GPU performance, of course, if your GPU cost is varying a lot over time, one of the ways you can help alleviate that is to do dynamic resolution. So your last frame, it was slow. Essentially, the idea is the current frame is going to be slow too. These aren't spikes. So you'll have like particles, fog, and smoke, or more draw calls, or explosions, or high density objects, something like that. Anything with a lot of alpha blending is going to be murder for your GPU. So dynamic resolution. It's been available since 421, and you may look at that and say, but Kelly, it's been available since like 417, which is completely true, except for PC. GPU timestamps on PC are very special. Essentially, because you have what consoles can use is they can basically use the graphics API. And because the OS is largely staying out of their way, that makes a lot of sense. They don't have these CPU bubbles. They don't have Windows Device Manager getting in their way. And because of that, the time they get back is the actual time. The problem is on PC, we have these occasions where you do get one frame spikes. And because of that, then your last frame was really long, but this frame is really short again. So now you've down-resed a ton, but you didn't need to, and it just looks like crap for no reason. This was something I heard a ton of people complain about at like GDC 2018, and it was so frustrating because I'm sitting there in the audience like, we have this. This is a thing. We can just give it to you. Pretty much all the IHVs have driver timing APIs. It's just a matter of like getting the hooks in there and making them work properly and integrate with that system really well. Which, if you've ever worked with driver APIs, is its own fun business. But essentially, the feature was formerly only available for console, is now available for Intel as of 421. So if you haven't tried it out, let me know how you like it. If it's working well, if it's not working well, let me know, and we'll make it work for you. So the other nice thing about dynamic resolution is that it's not just for the low end. What you can do is you can set your frame time budget, and you can set a max screen percentage. So actually, if you want to go higher, you could set that to 200%. And then if that person has the right hardware that can push all of that, then sure, they can go all the way up to 200%. Again, just keep an eye on all of your things that are working. Make sure the dynamic res is showing up there. The docs are very easy to use. This should be pretty much a no-brainer. And if it's not working, again, just let us know. We'll make sure it gets fixed. But this is something that essentially is just going to be naturally in the engine for you to use. It's also going to make your stat unit graph way more exciting, because now it's going to be all wobbly, and you have the percentages on there as well, or when it's switching to which percentage. And now for some exciting things yet to come. So dynamic resolution is really drastic. You're essentially crunching the entire frame. But we maybe don't want to do that. Maybe we have some like a really nice hero asset that now is a blurry mess. This is something I'm actually really excited about, which is called variable rate shading. The idea is that dynamic resolution rendering is reducing the amount of pixel shading work you have to do by downresing the entire scene. The reason it does that is because the hardware can only shade at one rate for the entire render target. It can only say, okay, if there's 1 pixel, I have to hit the pixel shader 1 time. What's essentially happened is now we have hardware that can get a command that tells it on a per object basis how fine you want to shade. So if you don't want to do the pixel shader every 1 time, 1 pixel, you want to do it maybe once every 2 by 2 pixels, and then apply it across that, you can do that as well, which is super handy for things like this. So if you have like an LOD system, you can down-res things in the background and keep everything up front really high res. If you have motion blur going on, why would you shade everything at high res and then put a motion blur on top of it? You're wasting pixel shader time. So essentially, as these real-time engines are getting more complex and more pixel shader bound, we can save a lot of this time by just using those resources in the place where we're actually going to see a visual difference. So essentially, what I've been working on partially is a variable rate shading integration into Unreal. It says CPS because originally we invented it in 2014 and it was called coarse pixel shading back then, but variable rate shading is a better name anyways. So basically, it's a super easy integration. The API commands with VRS are essentially 2 commands. It's just set shading rate. And because of that, so here I just applied it to pretty much everything, and it's hard to tell with projectors. It's definitely something that you want to look up the white papers for and really be able to tell for yourself. But it's very little visual difference. And part of the reason for that is because while variable rate shading is going to blur the outline, or while dynamic resolution rendering is going to blur the outlines of all of your shapes, variable rate shading is going to maintain all of those outlines, and it's just going to downres what's inside of the form. And the human eye is much more sensitive to silhouettes than it is to like high-res textures within that silhouette. So we can actually get back a lot of performance for relatively little visual difference. In this particular workload with Sun Temple, we got around like 1.3x speed up. I've seen around like 1.2 to 1.4. Very much depends on the workload and the implementation. This is kind of a hammer. But honestly, it's going to be a really exciting technique. So we're thinking about a few different places to integrate this naturally with Unreal so that you guys don't have to think too much about it. Candidates are like integrating with the LOD system, with depth of field, with motion blur and all of that to give you guys back a lot of performance, but also maintaining a lot of control, which is kind of what we're all about. So if you have all of you're rendering everything you want, you're spending your pixel shaders correctly, you've rendered your frame, fantastic, but now your AI is making everything horrible. I see this problem a lot, that people feel like they have to trade a ton of performance in order to get the anti-aliasing that they want, especially on the low end. People end up just turning it off. It's terrible for text, and so I have a present for you. Conservative morphological anti-aliasing, because we had to come up with another bunch of letters to throw in front of AI. It does actually work pretty well. Again, this is one of the features that I'm really excited about. Basically, CMA kind of specializes in text. It does an edge detection that works really well and maintains a lot of those outlines and those silhouettes that, again, your eye is really sensitive to, while still giving you a really nice quality bang for your buck anti-aliasing algorithm. So the quality is similar to SMAA, but you're looking around more like FXAA cost in terms of performance. This is essentially, like you can see on the top, again, with projectors, it's very hard to determine the actual quality of the image, so I invite you to go read the white paper by Philip Strugar. But essentially, we get this edge detection algorithm that then nicely smooths everything and gives us a really clear look at, a really clear and cheap look at anti-aliasing for our low-powered hardware. Awesome. Sweet. Well, I think I talked too fast because we're already back here. So we're going to talk about some common themes again. So we've talked about ways to trade our work between our GPU and our CPU, depending on the bottleneck. We had talked about ways that we can go wide, both on with the CPU in order to do both offline and real-time work. And there's also, we talked about ways to spend processing time where it matters, whether that's on the GPU and then shading the right number of pixels, whether that's moving workloads off the GPU to do things naturally. Like the vision I have for the future of Unreal, or the work that we're doing with it, is creating these really naturally scalable systems. Creating things that naturally can detect where you have headroom and move the work there to have like a nicely working system on as many platforms as possible with relative ease for you guys. And my ask for you is then, what do you think? Have you tried these things? Please try these things, especially the RHI thread. I think it's pretty much just a checkbox. I highly recommend you check it out, see if it removes some of your render thread bottlenecks. But also, this is an ongoing process. We've been working for Epic for years. We'll work with them for years to come. So if there's something that you care about in terms of low power performance or cool CPU things that you want to see, let us know. So I'm new to the Twitter, but those guys know what they're doing. So you can tweet at us, you can email us. Jeff Roos is also from Intel, and Rolando's at Epic. I'll be here for a little bit if you want to have a chat. And if nothing else, thank you guys so much for coming, and go make great stuff.